This is the start of Chapter 3, Section 3. We're going to cover the first half of this section today. It's dealing with subatomic particles and masses of atoms. You are going to need a periodic table handy, and you're going to need a calculator. So starting off with our subatomic particles, we start with the atom. So we've got Dalton's view on things. Everything is the smallest you can go is an atom. In the last section, we talked about the discovery of the nucleus and of the electrons, and now we're going to break all of that down for you. So contained within the atom itself, we have the nucleus. You should have the definition for the nucleus. It is that small, dense center to the atom that is positively charged. Within the nucleus, you have your protons and you have your neutrons. So protons have a positive charge. Neutrons are considered to be neutral or no charge. Outside of the nucleus, and again, the nucleus has most of the mass but very little volume. The electron or electron cloud is just the opposite. So the electrons are surrounding the nucleus. It is a much larger area in which they occupy, but they are quite tiny in their mass. And electrons have a negative charge. So he's introducing you to a couple more terms here. Again, most of the atom's mass is going to be in the nucleus. The atomic number is equal to the number of protons. Atomic number is equal to the number of protons. In this section, we are only going to talk about neutral atoms. So that means your protons will also equal your electrons for a neutral atom. Please look at your periodic table so you can get used to finding some of these numbers. If I am looking at carbon on my periodic table, its atomic number is that whole number just above the symbol. So carbon has 6 protons, and a neutral atom of carbon will have 6 electrons. Looking at another element, if you go find potassium, that symbol is K. Potassium's atomic number is 19, which also means it has 19 protons and 19 electrons for a neutral atom. And breaking protons down and neutrons down, we have another subatomic particle. Most of you probably have never heard of quarks, but we have our quarks, and we're going to go talk about those just a little bit too. So here's our quarks. We have 6 quarks, or 6 types of quarks. Every proton is made up of 3 quarks. Every neutron is made up of 3 quarks. But we are not going to go so far in depth as to what the arrangement of those 6 quarks have to be for your protons and or your neutrons, because it can change. But those 6 names that you see outlined in white, up, down, charm, strange, top, bottom, those are the names of the 6 quarks. You do not need to memorize that part. I am more interested in you knowing that quarks are another subdivision of your protons and neutrons, and that 3 quarks are needed for each. So here we are moving on. We're still in Chapter 3, Section 3. We're going to concentrate on the masses of atoms now. The mass number is equal to protons plus neutrons. Protons plus neutrons. This is always a whole number, and it is not on your periodic table. So if I go back to what we had just talked about previously, getting our important information in there, your atomic number is equal to protons. It's also equal to the number of electrons. So your mass number is equal to protons plus neutrons. That is quite important too. For the math that we're going to be doing today, it's not hard math, but math nonetheless. And if I look on my periodic table, for instance, let me just go take a picture. Looking at this periodic table, there are lots of masses. These numbers that are at the bottom, different highlighter color, let's see. The numbers at the bottom here of each one of these, that is considered its average atomic mass, not its mass number, and we will get into how to calculate the average atomic mass, which is going to give you some type of decimal value. But right now, a mass number is concentrating on one isotope of an element, and what that whole number mass is for your protons and your neutrons are. Again, previous section, we said that the relative mass of each of these, the proton is a 1, the neutron is a 1, the electron is essentially 0 or negligible mass for the electron. That's why we're working with whole numbers here. For your isotopes, these are going to be atoms of the same element with different mass numbers. Atoms of the same element with different mass numbers. And we have two types of notation we're going to look at for the different isotopes. The first one is called a nuclear symbol. You don't need that star pattern around it. That's just for the black background. But the 12/6c, the top number is always the mass number. Again, that's protons plus neutrons. The bottom number is always the atomic number, which again is equal to number of protons, which is equal to number of electrons. And then your element symbol, so this has to be talking about carbon. We're going to work through several of examples. So again, this is our nuclear symbol information here. At the bottom, they have changed that into hyphen notation. That is carbon -12. And again, you've just spelled out what the element is and the 12. This 12 and this 12 are the same value, so that is the mass number. So your element hyphen whatever the whole number mass number is that you have calculated. So you've got a nuclear symbol, you have hyphen notation, and you've got a couple of equations to go with for mass number and atomic number so that we can do some of these calculations. This is looking at two of the isotopes of carbon. It's not the only two. Carbon-12 is our typical carbon. It's got 6 neutrons, 6 protons, 6 electrons, because if they give you carbon-12, you can look at your periodic table. So you would have a periodic table to look at. You would find carbon, and carbon's atomic number is 6. That's how you know it's got 6 protons, 6 electrons, and then doing just a little bit of math, since your mass number equals protons plus neutrons, if your mass is 12, and again, that mass was given right up here, your number of protons from the periodic table is 6. That is your atomic number. You calculate the number of neutrons. So 12 minus 6 equals 6. That's how many neutrons you have. The other isotope of carbon you see here is carbon-14. It's the one used for radioactive carbon dating. And notice your numbers are a little different, but we also have a different mass number. It is 14. So carbon is still carbon because the atomic number is unique to carbon. So carbon has to have 6 protons to be considered carbon. Again, you find that on the periodic table. But if I go plug in my numbers again, this time it's 14 minus 6 to give you 8. It has 8 neutrons. With the number of neutrons changing, the properties of your element do change. And again, one's radioactive, one is not, but it is still fundamentally carbon. Most of the elements on the periodic table have one or more isotopes. Most of your elements will have one or more isotopes. So going through this example here, just writing down a couple things as a reminder or a refresher. We've got our mass number, which is equal to protons plus neutrons. We have our atomic number, which is equal to the number of protons and also equal to the number of electrons. So when I look at chlorine-37, I see right away this hyphen 37. That has to be the mass number. And for the fact that it is actually chlorine, I'm going and finding chlorine on my periodic table. That's Cl. And its atomic number is 17. Please verify on your periodic table. Atomic number 17. That also means the number of protons is 17 and the number of electrons is 17. To find the number of neutrons, we are going to do a tiny calculation. Our mass is 37. Our number of protons is 17. We calculate neutrons by subtracting 37 minus 17, and we get 20. So hyphen notation was given. Now if I asked you to convert this to a nuclear symbol, the nuclear symbol, the symbol for chlorine is Cl. The top number has to be the mass number, 37. The bottom number is the atomic number, 17. So there is your nuclear symbol. Moving on over to relative atomic mass. If you think of the word relative, that means related to, if in relation to. We're going to look at how different elements are related to each other to come up with these atomic masses that everybody agrees on. So the carbon-12 atom, there's its actual mass in grams, and we're not going to work with any calculations in this chapter with numbers like this, but it's just so that you're aware that is the mass of a carbon-12 atom. And we have a new mass unit. It's called atomic mass unit, or AMU. You're used to masses being in grams, kilograms. You've heard those units before. AMU is a little different. It is a mass unit, but we're going to use that mass unit, AMU, when we are talking about atoms or things on the atomic level. Very, very, very tiny. 1 AMU is equal to 1/12 the mass of a carbon-12 atom. So if you did just a little bit of math real quick, 1/12 of 12 is equal to 1. So that's how they get the 1 AMU, is 1/12 the mass of a carbon-12 atom. And our carbon-12 atom is the mass that is being used where masses of all other atoms are based off of its mass. They did try to use a couple other elements early on, but because of reactivities and other issues, carbon-12 was eventually settled upon. So carbon-12 is going to be the standard that all other masses are calculated off of for other elements. That being said, looking at the proton, neutron, and electron, you have seen these values before, but we have rounded them off. So the relative masses for each of them we are saying is proton is 1, neutron is 1, and the electron is 0 because its mass is negligible compared to the proton and neutron, because the electron is about 1/2000th the mass of a proton or neutron. Calculating average atomic mass. These average atomic mass values are what you actually see on the periodic table, and it takes into account a weighted average of all isotopes. So if carbon has isotopes for carbon-12, carbon-13, and carbon-14, then we're going to take the weighted average. By weighted average, it's how abundant is that particular isotope going to be, say, out in nature. Carbon-12 is extremely abundant, whereas carbon-13 and carbon-14, there's minor amounts of those. A lot of elements are like that, especially with your hydrogen, because you have a hydrogen 1, hydrogen 2, and hydrogen 3. And other elements are going to be split a little more evenly. But this value is on your periodic table, and we are rounding to 2 decimal places. So your average atomic mass, here is our formula for it. Takes the mass of your first isotope times its percent abundance, plus the mass of the second isotope times its percent abundance. Let's say you had a third isotope. You would just keep going. You would take the mass of the third isotope times its percent abundance, and all of those percentages should add up to 100%. So you divide by 100. If there's 4 isotopes, great. Just continue to add on to your numerator. We're going to go work out a couple of different examples. So as I look at this one right here, it says calculate the average atomic mass of oxygen. Oxygen's got 3 different isotopes, oxygen 16, which is very abundant, and then oxygen 17 and oxygen 18. So you would set up your equation. You have the equation from the previous slide. You would write it out and start plugging in information. This is how it is plugged in. So we've got the mass of each one times its percent abundance. Notice the percentages are still left in percent form, and they add up to 100. Please put this into your calculator to make sure you can get the correct answer. Order of operations is important. Order of operations is important. So as a quick reminder, you will multiply these two, multiply these, add up those top 3 values, and then divide by 100. Your final answer is 16.00 AMU. Another variation of this, instead of it being out of percentages, they say, okay, you've got 10 atoms of chlorine, 8 of every 10 are chlorine 35, that's one isotope. 2 of every 10 are chlorine 37, that's the other isotope. So we have 2 isotopes we're working with. And again, you could change this to percentages, but they're putting it in a little different. They're doing the 8 and the 2. 8 plus 2 is 10. That's why you see 10 on the bottom. If you chose to work this out as percentages and did that as 80%, 20%, and then 100 on the bottom, mathematically you would still get the same answers. Again, plug this into your calculator. Make sure you can get the right answer. And your answer is 35.40 AMU.